So hopefully by now you feel pretty comfortable with the idea of a differential equation and relatively comfortable solving them, right, for both general and particular solutions. So before we start this next topic, let's find the solution to the differential equation dy dx equals x minus y. And I had mentioned that as far as the scope of this course is concerned, we only cover solving separable differential equations, so that's how we're going to start. We are going to try to separate our variables. So let's see, x minus y. And since the dy is in the numerator on the left, that side is going to be my y side. So I'll begin by adding y to both sides. So that will leave me with dy dx plus y equals x. And then the last thing to do is just multiply both sides by dx to bring that dx over to the right. And I'm actually going to take the time to write this out here, and you'll see why. So multiply both sides by dx, which leaves us with, okay, well, when I distribute the dx to this first term, the dx's on top and bottom cancel, and I'm left with just dy. And then when I distribute it to my second term, I am left with y dx, and then x dx on the right. And now, hopefully, you realize we have a little bit of a dilemma. My right side is looking good, but my left side still has y's and x's mixed up. And the fact that these two are sort of conjoined right here, we're not actually going to be able to separate them. I invite you to try this, right? To try and manipulate this enough so that you get the variables separated. If you can do it, let me know. But as of right now, we can't. Now, this doesn't necessarily mean that we don't know anything about this differential equation. While we can't solve it using separation of variables, there is a way that we can get a sense of what the solution looks like without having to solve it analytically. And we do that with something called a slope field. Now, don't worry about what a slope field is right now. I just want to direct your attention to the differential equation itself. And let's think about what this equation actually says. Yes, it says the derivative of my function is x minus y, but think about what that really means, right? Derivative just means the slope of the tangent line, right? So what this differential equation actually tells us is that my slope at any point is my x-coordinate minus my y-coordinate. So if we can calculate the slope of the tangent line at different points in the coordinate plane, maybe we can start to create a picture for ourselves about what this solution curve or family of solution curves might look like. So for example, suppose I wanted to know what is the slope of the tangent line of my function at the point 2, 0. All right, so I want to know the slope at the point 2, 0. Well, I look back to my differential equation and say, oh, well, the slope is given by your x-coordinate minus your y-coordinate. So in this case, that would be 2 minus 0, which equals 2. So let's head on down to this grid right here, and let's show that the slope at the point 2, 0 is 2. So the point 2, 0, right, and a slope of 2, well, a slope of 1 would be like a 45-degree angle, so let's just do a little bit steeper than that. Here we go, and that's all we do. We just draw a little slope of a tangent line. All right, let's get the slope at a different point. Let's maybe get the slope at the point, oh, I don't know, -1, +2. All right, so again, our slope is given by x minus y, so that would be -1 minus 2, which is negative 3. So let's come on back down. Let's find the point negative 1, positive 2. Negative 1, positive 2, and let's show that our slope is a negative 3. So it's going to need to be a little bit steeper than the line that we previously drew, but it will have a negative slope. So maybe like this. Again, you're not going for pinpoint accuracy. You're going for sort of a qualitative effect here. All right, now let's see. How about the slope at the point 1, 1? Well, since our slope is x minus y, that will be 1 minus 1, which gives us 0. Okay, so at the point 1, 1, I need to indicate a 0 slope, which is a horizontal line, right? The tangent line at that point would be horizontal. In fact, if we look back at the differential equation, we realize anywhere that x and y are equal, our tangent line will have a slope of 0. All right, so at the point 1, 1, 2, 2, 0, 0, negative 1, negative 1, etc., etc. So let's do that. Let's show that any place where x and y are equal, my slope will be 0. So we did 1, 1, so here would be 2, 2, whoops, 0, 0, negative 1, negative 1, negative 2, negative 2. And we're actually going to complete this whole thing, all right? And that's the purpose of this chart over here, all right, to fill out corresponding x and y coordinates and then calculate the slope and transfer those slopes onto the grid. All right, so we'll do a few together and then I'll let you finish the rest on your own. So this grid spans from negative 2 to positive 2 in both x and y directions. So we'll begin with x equal to negative 2 and y equal to negative 2, right? X equals negative 2, y is negative 1, x is negative 2, and y is 0. X is negative 2, y is positive 1, x is negative 2, and y is positive 2. Okay? So then if we were to calculate the slopes, again, it's just x minus y. So for our first column, negative 2 minus negative 2 is 0. Negative 2 minus a negative 1 is negative 1. Now that one we don't have plotted yet. All right, so at the point negative 2, negative 1, all right, my slope should be negative 1. So here's the point, negative 2, negative 1, and my slope is a negative 1. So that's going to be like a 45-degree angle, but with a negative slope. So maybe like that. Okay? Now, at the point negative 2, 0, well, negative 2 minus 0 is negative 2. So at the point negative 2, 0, my slope is negative 2. So a little bit more steep than what I previously just drew. So maybe like that. Okay? Now, at negative 2, 1, well, negative 2 minus 1, that's negative 3. Okay, so at negative 2, positive 1, that's negative 3, so we got to get even steeper still. It's still a negative slope. And notice, you don't want to leave yourself with nowhere to go, right? If your slope of negative 2 is super steep, when you have to draw a slope of negative 3, you're going to sort of run out of room. All right, and then at the point negative 2, 2, well, negative 2 minus 2 is negative 4. All right, and that would be the point up here, and so pretty darn steep. There's sort of only so far you can go with this. All right, great, so that took care of the first column of our coordinate plane. Let's do the next one. So let's do when x is negative 1, and you can do these in any order that you like. I just find this to be the easiest to keep track of. So x is negative 1 everywhere in that column, and we'll let y span its entire range here. Okay, so at negative 1, negative 2, well, negative 1 minus a negative 2, that would be a positive 1. So let's come to that point and indicate a slope of positive 1. Here we go. All right, we already know that at the point negative 1, we have a slope of 0. Negative 1 minus 0 is negative 1. So let's come to the point negative 1, 0 and indicate a slope of negative 1. So maybe like this. And then at the point negative 1, positive 1, well, negative 1 minus 1, that's negative 2. So maybe here's a slope of negative 2, about, okay? And then the last one we already did, but we'll write in the number. Negative 1, 2 gives us a slope of negative 3. All right, so what I'm going to do is complete the rest of this table, fill in the corresponding slopes on the grid. All right, you can pause the video, work through them yourself. In fact, I recommend that you do to make sure that you have the right idea and that your picture comes out looking roughly like the one that I've created. So go ahead, give a pause, and I'll see you at the finish line. Okay, so hopefully you had a chance to complete the chart, drop your slopes into the coordinate plane, and hopefully your picture looks something like the one you see here, maybe even a little bit better than mine. All right, but now you can see why what we've created is called a slope field. It is literally a field of slopes. All right, and these little lines represent the slope of the tangent line at the given points. So if you think about the fact that we're looking at the tangent line, right, and knowing what it means for a line to be tangent to a curve, you could maybe start to picture what one of the solution curves would look like if we were to draw it in. It would have to sort of follow those tangent lines all across the grid. And we'll get some practice drawing in solution curves later, but for right now, I'd like us to get comfortable with generating slope fields ourselves. So let's go to the next page. Okay, so we're going to create a slope field for the differential equation dy dx equals 1 over x. In other words, the derivative, the slope of the tangent line at any point, is given by 1 over your x coordinate. This might look a little bit intimidating because this grid now spans from -4 to +4 in both directions, right? But it's actually going to be not as tedious to complete, and that's because our differential equation is only dependent on x, all right? And you'll see how that helps us, all right? So let's start filling in our chart. So anywhere where our x-coordinate is -4, our derivative, the slope of our tangent line, is going to be 1 over -4. So -1/4, right? Anywhere that our x-coordinate is -3, our slope will be 1 over that. So -1/3, right? -1/2. Right? When x is -1, 1 over -1 is just -1. Interesting, right? When x is 0, our slope given by 1 over 0, well, that's going to be undefined. And we'll talk about what we do there in just a moment. When x is 1, our slope is 1. And then when x is 2, our slope is 1/2, and so on and so forth. Okay. Now, let's transfer these onto our coordinate plane. Now, notice for this first column here, it says anywhere that x is -4, our slope is -1/4. So that means that all along the vertical line, x equals -4, anywhere that x is -4, our slope is -1/4. All right, so we're going to draw, all right, a negative slope and pretty shallow. Okay, I'm going to try my best. I can only do so well with this stylus here. All right, so notice that's a place on the coordinate plane where x is -4. Guess what? So is this. And so is this. Right? Everywhere here. X is -4. So my slope is -1/4. Now, for better or worse, all of those slopes should be of the same steepness. That slope at -4, 0, looking a little bit suspect, but you got to cut me some slack here. All right, so this is actually going to go very quickly, right? Since our differential equation only depends on x, right, we can just take it column by column. All right, so great. When x is negative 3, anywhere x is negative 3, my slope is negative 1/3. All right, so still negative, little bit steeper than negative 1/4. I'm gonna do my best here again. So maybe like this. You should be able to manage much better than I can. But that is sufficient. Those should be straight lines. Okay, let's move on to x equals negative 2. My slope is negative 1/2. So a little bit steeper still. Again, we don't want to go too steep too fast and leave ourselves with nowhere to go. Okay. And then when x is negative 1, my slope is negative 1. All right, so that's kind of like my 45-degree angle right there. Okay, so here we go. Roughly like this. Okay. Now, I'm actually going to skip over the 0 column because maybe we'll be able to see what should be happening anyway, but we'll come back to it. All right, so now when my x-coordinate is 1, everywhere where x is equal to 1, my slope is positive 1. So let's draw that in. Again, that's like a 45-degree angle. I don't know why I'm finding it so much easier to do it this way. Oops. Okay, and then when x is 2, a half, so less steep. And then 1/3, even more shallow still. And then when x is 4, 1/4, even more shallow. Like maybe almost horizontal. Okay, now you can maybe kind of see where everything is going, right? It's often said that you can think of a slope field like a stream, right? And that the slopes are sort of like the current. Where is everything being pushed? And if you look at the slope field, it looks like everything is sort of being pushed down towards the y-axis, right? And so now let's come toward that 0 column. Our slopes are undefined, so you have a choice. All right, you can just leave it blank. Sometimes that is what your textbook or the AP exam will do, or you can do what we know is happening, right? When a slope is undefined, it's because that slope is vertical, all right? And that's sort of what I prefer. I prefer to draw in vertical lines here, all right? These should be right on the x-axis. Again, I'm trying my best. All right, and then doesn't that sort of complete the picture of where it looks like things are going? All right, so if you have an undefined slope, you can either leave it blank or you can make a vertical line. I think either is acceptable. All right, so there you go, slope field, done. All right, let's move on to example 2 and create a slope field for dy dx equals y minus 1. In this case, our derivative, our slope, only depends on y. Right? Doesn't matter what x is. Anywhere where y is negative 4, our slope will be the same value for all x values. Okay, so let's get cracking. Alrighty, so when y is negative 4, oh boy, we're going to have all of our slopes work out to be negative 5. All right, when y is negative 3, they're going to be negative 4, right? And all it says, it's 1 less than your y coordinate, so we can just kind of plow right on through here very easily and make quick work of it. All right, so let's plot these. All right, so everywhere where your y coordinate is negative 4, my slope will be negative 5. All right, so that's going to be all along the horizontal line, y equals negative 4. I will have slopes of negative 5, which are going to be negative and very, very steep. So we'll do like this. That's not even terribly steep, but you get the idea. then everywhere that y is negative 3, my slope is negative 4. So still negative, maybe slightly less steep than what we previously drew. Again, got to leave ourselves somewhere to go. When y is negative 2, slopes of negative 3. Okay. When y is negative 1, my slope is negative 2. And then everywhere that y is 0, my slope is negative 1. And now everywhere that y is 1, my slope is 0. So that's your horizontal line. And then for y equal to 2, all of our slopes will be positive 1. Everywhere where y is 3, slopes are positive 2. And for y equal to 4, our slopes are positive 3. Okay, and so again, hopefully you can start to get an idea of what it would look like if we were to pick a point at which to start and then follow the tangent lines across the coordinate plane, what that might look like. But there's also something interesting to note here. All right, notice that because our slopes in this case only depended on y, there was no x coordinate involved. Notice what happened to our slope field. All right, the little tangent lines were arranged in rows, right? They were the same all the way across individual rows, okay? And that sort of makes sense, right? Because it was only dependent on y, we ended up with horizontal patterns, okay? Whereas if we come up to this example 1 right here, our slope was only dependent on x, and now the slopes arranged themselves in columns. They were identical across an entire column. Again, sort of makes sense. Since it was only dependent on x, they arranged themselves in these sort of vertical patterns. Just something interesting, worth noting. Okay, let's move on to the next page. All right, so now, all right, we'll go from generating a slope field ourselves to working with an existing slope field and sketching in a particular solution. All right, so here we have a differential equation, right, dependent on both x and y. All right, when it's dependent on both x and y, that's when you don't see any sort of columns or rows happening. You just sort of see this general sort of spreading out and everything's different everywhere. All right, so we have its slope field, all right, and then we are asked to draw in the solution curve that passes through the point 0.8. All right, so we want to be passing through this point right here. Okay, and also the fact that there are arrows in this slope field doesn't matter. You can draw the arrows, you don't have to. All right, so we want to pass through the point 0.8. So that means we're going to need to draw a curve that goes through that point and follows the slopes of our tangent lines across the entire graph. All right, now it doesn't mean that we need to pass through tangent lines. All right, it doesn't mean that we always have to be touching a tangent line, because technically there's a tangent line everywhere, right? We just can't draw a tangent line everywhere or the grid would be solid black. Okay, so you just need to literally go with the flow. Go with the flow of the tangent lines and you'll be okay. So that might look something like this, like, okay, right, things are going this way. But then we also need to extend the other direction. So let's come over here and as best I can, all right, sort of like this, okay? And that's good, all right? Again, we don't need to be hitting a tangent line every single step of the way. We just need to be moving in the right direction. It should look like our curve's slope agrees with the slope of the tangent line at any given point. Okay? Now, let's draw in the solution curve that passes through the point 0, negative 0.8. So we'll use a different color. All right, we want to be passing through the point here and then going with the flow of the arrows. All right, so as best I can again, here we go. So, right, things are generally trending this way, but then I also need to extend in the other direction. All right, so sort of keeping in mind where the arrows are going. There we go. All right, notice I didn't get like completely horizontal because I did not see my slopes going completely horizontal. All right, so the curve in blue is one particular solution for our differential equation up here. The curve in red is another particular solution. So each of those would represent the solution that you would get for different values of C. Okay, not too bad, right? And then I think there's some more practice on the next page. Okay, so for example 4, we have the differential equation dy dx equals negative x over y. Sketch the particular solution that passes through the point negative 3, 0. Hopefully you can kind of see what the solution curve is going to look like. It's kind of right there for you, right? But let's draw it in just in case. So let's start at negative 3, 0 and follow the slopes, okay? So roughly like this. Around, around, around. And now there's sort of a point of discrepancy here. All right. Well, first of all, this is actually the slope field for a family of circles. All right. The function y that you would get would be a circle. However, we know that the graph of a circle is not a function. So you could choose to just graph the bottom portion. And something else that I think sort of confirms that that's the right thing to do is the fact that when you get to the other side, right, when we got to the point positive 3, 0, notice the arrows were sort of shoving us back down in the other direction. So that to me is sort of an indication that we stop here, right? Now we're not going with the flow of the arrows. In fact, we would be going against it. But some people like to go ahead and, you know, draw this other portion of the circle in right here, you know, because it is a circle, right? This is a differential equation that describes a circle. So I won't nitpick. I'm kind of okay with either. We can always discuss further in class. Okay? Alrighty, example 5. Here we go. The differential equation is y prime equal to 2y. Here's its slope field. Again, notice this is only dependent on y, so the slopes have arranged themselves in rows. Across an entire row, every slope is the same. So sketch in the particular solution that passes through the point negative 1, positive 1. So that would be right here. Okay? And again, we just need to go with the flow. Alrighty, so looks like as we move off to the right, things are going upward. And then as we come off to the left, things are sort of flattening out, right? Because if you look on the x-axis, you see horizontal slopes. All right, so we need to come down this way. We still need to follow the slopes, but then eventually we need to sort of get to a slope of 0. Again, that should all connect. I hope your picture is better than mine. All right, but that's the idea. Okay? Alrighty, let's move on. Okay, so now that you've seen some examples of differential equations, right, and their corresponding slope fields, right, you sort of maybe start to see that the slope field kind of looks like the graph of the solution curve. That's the whole idea. All right, so in part 3 here, we have a bunch of different slope fields, and at the bottom, a bunch of different solution curves. Notice, these are not differential equations. Why not? Well, because there's no derivatives in them. It's just y equals, right? So these are solution families. And we're going to see if we can match the solution family to the slope field. And this is pretty easy because the slope field should look like the graph of the solution family. So I actually think it'll be easiest to start with the letters and match them up with the numbers. All right, so for letter A, the family of curves y equals c. That would be a series of horizontal lines, right? Such as like y equals 4, y equals -2, y equals 7, right? Those are just going to be horizontal lines. So let's just find, aha, there it is, number 4. All right, so it looks like letter A matches up with slope field number 4. All right, and let's just cross that one off, right? We've used it. Great. All right, let's look at B. Now we've got y equals x plus c. So for example, y equals x plus 3, y equals x minus 8. All right, oh, it's still going to be linear, right? So we want a slope field that looks like a linear function. And it's kind of staring right at us there in number 8. All right, so function B matches up with slope field 8. Good. Okay, now for letter C, y equals x squared plus c, right? All we really care is that that function is going to be parabolic. So we want a slope field that looks parabolic. And I would say the closest thing we have is graph 3, right? That looks like it could be a parabola, right? Sort of like doing this, okay? So graph C, or rather function C, with graph number 3. And then for function D, y equals x cubed plus c. All right, again, great. Our graph should merely look cubic. Now, we've actually got maybe a couple choices here, but if you look closely, not really. All right. Graph 2, it waves, but that's not cubic, right? Maybe if it were degree 4, we would choose graph 2. Graph 5 could potentially be cubic, but it looks like it's continuing to wave, so not that one. I think our best option is slope field 6. All right, that looks like it could be cubic. All right, so letter D goes with slope field 6. Okay, I'm actually going to skip over E for now, and you'll see why. All right, but let's come to graph, function F. All right, sine x plus c. Again, that just means, right, sine x plus 2 or sine x minus 5, right? They're just going to be vertical shifts of one another. All right, so let's find something that looks like the graph of sine. All right, now again, we've got two options, slope field 2 or slope field 5. And really this just comes down to knowing the graphs of sine and cosine. The graph of cosine is an even function, right? It's symmetric about the y-axis. Sine is an odd function, right? Symmetric about the origin. Slope field 5, that's the one that we want. Alrighty, so here we go. And then we pretty much just selected the correct answer for letter G. That was slope field 2. Right, that looks like the graph of cosine there. Alrighty, now we've got two remaining, E and H. Okay, now that's the difference between 1 over x squared plus c and ln of x plus c. All right, and if you know your graphs, right, got to know your pre-calc, all right, this is sort of an easy choice. All right, letter E corresponds with graph number 1. Right? This is sort of our graph of 1 over x squared, right? Again, an even function. All right, so letter E goes with slope field number 1. leaving number 7 as the slope field for letter H. And notice, all right, it's ln of the absolute value of x, so that we are allowed to get values on the negative side of the coordinate plane here, right? Typically, the graph of natural log just does this, but by saying the natural log of the absolute value, we can get this other half of the graph as well. All right, so matching up the slope field to the solution family should be very easy. That's the whole point. The slope field is supposed to look like its solution family. Matching up the slope field to the differential equation, that's a little bit tougher, but there are some tips and tricks along the way. Okay, so unfortunately, there is no prescriptive way to do this. There's no sort of hard set of rules. There are only strategies, and I share a few of my favorites with you now. All right. So the first tip is to look at the differential equation and the slope field and identify where do I have undefined slopes, right, vertical slopes, and where should I have undefined slopes based on the formula. If you can match that up, that's going to help narrow it down for you. Also, looking for zero slopes, horizontal slopes, that's going to be your friend as well, right? If you can figure out where they are on the slope field and where they should occur based on the differential equation, that's going to narrow down the pool of candidates as well. So let's take a look at example 6, all right? And you've been given a slope field and then a number of candidates for the corresponding differential equation. All right, so I'm just going to go through each of the differential equations and see what we can say about them. All right, and actually the first thing I'm going to do is rule out option C. Why might I rule out option C right away? Hopefully, maybe you're thinking, well, if my differential equation is only dependent on y, my slopes should be arranged in rows, like this, right? So all across one row, the slope should be identical. Remember? And clearly these are not. So it is not option C. All right, and A and B look kind of similar. So let's figure this out. All right, so for option A, all right, well, I notice that I have a y in the denominator. So if y were ever to equal 0, right, if y equals 0, that would mean that my derivative is undefined, which would mean that I would have vertical slopes. So anywhere that y is 0, I should have vertical slopes. Well, y is 0 all along this line here, and those are not vertical slopes. So I'm going to say pretty confidently it is not option A. Well, let's hope that it's option B, and it is, and let's think about why. Okay, so here, all right, notice now that I have an x in the denominator. So when x is 0, that should tell me that my derivative is undefined and my slopes will be vertical. All right, so in other words, when x is 0, I have vertical slopes. Well, here's the line, x equals 0. And do I have vertical slopes? Well, there's nothing drawn there, but based on what's happening around it, you could pretty reasonably infer that, yeah, those are vertical slopes all along the y-axis. All right, now let's figure out when my slopes should be 0. All right, so if we're working with the differential equation dy dx equals negative y over x, right, when will my slopes be 0? So let's replace my slope with 0. Alrighty, when you cross multiply, you get when y equals 0. Okay? So now, all along the line, y equals 0, I should have 0 slopes, horizontal slopes. And I do, right? We figured that out right over here. Okay, so that's why option B is the correct choice in this case. All right, let's try another one. Okay, so here's a slope field. All right, and here are our choices. Now, this one should actually be very easy, but we'll go more in depth and talk about why, okay? So now notice, all right, let's actually start with option C. Option C is a differential equation that only depends on y. So if it's only dependent on y, our slopes should be arranged in rows. Across a single row, my slopes should be identical, and these are not. Sorry, C. All right, let's take a look at B. All right, this differential equation is only dependent on x. And when that's the case, my slopes are arranged in columns, all across one column. Any one that I pick, my slopes should be identical. And clearly that is not the case here, so it is not option B. So my only remaining option is A, all right, but let's just take a look and remind ourselves of how A does meet all the criteria. So I'm just going to take all of this away so we don't muddy up our picture. All right, and now let's start thinking about when would we have an undefined slope based on differential equation A? Well, we wouldn't, right? There's nothing in the denominator, there's no problem. So we should never see vertical lines, which I don't, all right, or blank spaces, which I don't see. All right, now when would my slope be 0? Well, let's find out, okay? When would my slope be 0? And with just a little bit of algebra, you can see that my slope should be 0 when y equals x. All right, so that actually gives you a line to look along, right? Anywhere where your x-coordinate and y-coordinate are equal, your slope should be the same. All right, so here's the point 0, 0. Here's the point 5, or rather 0.5, 0.5. Here's negative 0.5, negative 0.5. So let's look along this line and see if we think that the slope is 0 along that line. And, you know, barring any artistic errors on my part, I would say pretty confidently that, yeah, we are going through horizontal lines. All right? So not only is A the best choice because B and C don't work, right, but A matches up with where our 0 slopes should be found. Okay, so now on the next page, we'll get some practice matching up slope fields to their differential equations. Now, if you feel confident at this point, you are welcome to just skip through this video, do the work yourself, and then check your answers at the end of the video. But if you still feel a little bit unsure, you're welcome to stick along for the ride, kids, okay? So here's a bunch of slope fields, fun, 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 and a bunch of differential equations, alrighty? So I'm just going to start tackling the differential equations, easiest first, all right? And I think the easiest ones to handle will be the ones that are just dependent on x or just dependent on y. So let's start with f. All right, f is just dependent on y. That means that my slopes should be arranged in rows. So I'm going to look for a slope field where if I draw a circle around a single row, any row, all of my slopes are the same. So let's just browse. I don't think it's any of these bottom two. And then, okay. Actually, 11 is the only decent choice here, right? If I select any arbitrary row, all of my slopes across that row are identical. So that would signal to me that my differential equation is only dependent on y, and differential equation f is the only one that is strictly in terms of y. So slope field 11 goes with differential equation f. Great. All right, now let's go to letter A. That's the only differential equation that is solely dependent on x. All right, so that means that my slopes should be arranged in columns, right? They should be sort of arranged vertically. Across any vertical line, my slope should be identical. So let's just take a quick scan through these and see if any of these meet the criteria. Not 13. It could be 14. Definitely not 12. Definitely not 10. And let's see, 9 is tempting, but if we just take a look, like let's select this row right here, notice my slopes on the bottom much steeper than my slopes on the top. So I think it's actually not slope field 9. I think my best choice is graph 14. Let's just confirm, right, that across any column, my slopes are identical, and they are. All right, and notice something else. All right, where should I see 0 slopes in this differential equation, right? When does my slope work out to be 0? Well, my slope is 0 when x is, what would that be, -2? Right, if x is -2, my slope works out to be 0. And where do I see my 0 slopes? Well, right along this line, which is, I mean, if this is -2.5, I would believe that that's around x equals -2. So again, this is a good candidate right here. Okay, now from here, it's up to you what you wanna do. All right, let's just go to letter B. All right, so I know that when y is equal to 0, I should have undefined slopes because that would put a 0 in the denominator. All right, so I'm going to look for vertical slopes or nothing everywhere that y is 0, so all along the x-axis. All right, 13 is not a good candidate because it looks like I have 0 slope along the x-axis. It could be 12. 10 is not a good candidate for the same reason that 13 is not. I have 0 slopes along the y or the x-axis, and definitely not 9. So I think it's 12. Alrighty. And yeah, so notice, right, that everywhere that y is 0, I have vertical slopes, or there's just a blank spot. All right, but notice, all right, if you look back at the differential equation, my slope should be 0 when x is 0. Oh, so all along the y-axis, I should see slopes of 0. And again, it might not be exact. They might not have selected exactly x equal to 0 to draw slopes at, but, you know, roughly speaking, we're in good shape. All right, so I would say that 12 goes with letter B. Okay, let's do one that was similar to B. All right, let's do E. All right, now it's sort of the flip case. All right, in letter E, I should see undefined slopes when x is 0. So all along the vertical axis. Well, that's definitely not happening in 13. And in fact, now the only choice is 10. All right, so, all right, but notice, slope field 10 also has 0 slopes in the right location, right? In letter E, my slope will work out to be 0 when y is 0. In other words, all along the x-axis, and we definitely see that happening here. So our vertical slopes are in the right place, and our 0 slopes, our horizontal slopes, are in the right place. Okay, now let's move on to, let's do D, okay? Now we start to think, okay, when are my slopes going to be undefined? Well, never, because we don't have a denominator. All right, well, when are my slopes going to be 0? Oh, Well, my slope will be 0 whenever x is 0 or whenever y is 0. All right, so I should see horizontal slopes all along the x-axis and all along the y-axis. Number 13 is pretty convincing, and number 9 is tempting again, right? But notice, if I look along the x-axis, my slopes are not consistently 0, right? Sort of toward the edges, they start to, steepen, all right? So I don't think it's number 9. So let's go back and just confirm why 13 is the correct choice, all right? Everywhere that y is 0, I see horizontal slopes, but also everywhere that x is 0, right? Right around here. And again, you might not see exactly horizontal lines. The point is the graph should look like it's turning around, right? If we have a 0 slope, we have a turning point, okay? So this one fits the bill, all right? And now, of course, that leaves function C, differential equation C, having to match up with slope field 9. But let's see why exactly this is going to work out. All right. Good. So let's cross this one off. All right. And now for graph C, this differential equation will never be undefined. There's no denominators. It's not an issue. All right. Let's figure out where we would have 0 slopes. All right. So let's say 0 should equal x plus y. When is my slope 0? And again, with a little bit of algebra, we can see that when y is equal to negative x, when x and y are opposites, my slope will come out to be 0. So that gives us a line to look along, the line y equals negative x. So let's just plot that line. So 0, 0 would be on that line. So would the point 0.25, negative 0.25, as would negative 0.25, positive 0.25. All right, and let's just sort of create that line as best we can and see if our slopes appear to be 0 along that line. And yes, I think we are in good shape, right? It's not so obvious when your 0 slopes aren't stacked either in columns or arranged in rows, but they're there. All right, so I would say that slope field 9 is the perfect match for differential equation C. So hopefully this gives you some helpful strategies for matching up a slope field with its corresponding differential equation. If you had paused the video at the beginning of this page and worked through it yourself, I hope this worked out in your favor. If not, you might want to back it up and watch the tutorial. All right. Otherwise, I recommend that you try the suggested exercises. There's not that many. And congratulations, you just finished your spring break work.